The following video is going over problems 3, 4, and 7 from the 5.2a worksheet. And problem 3 says human blood type are O, A, B, or AB, but the distribution of blood types varies by race. Here is the distribution of blood type among black people in the United States at random. And we're asked, why is this a legitimate probability model? Now in that case, when you're thinking about it, we had two different conditions that had to be checked in order for a probability model to be considered legitimate. And the first condition was that all the probabilities had to be between two numbers. And probabilities are always between 0 and 1. So if we look at the distribution on the right side, all the probabilities are between 0 and 1. So it meets the first condition. The second condition is that the sum of the probabilities must all be 1. So if I were to add all these numbers together, I have to check, do I in fact get 1? And in this case, when you do add them together, you do get 1. And so we have the conditions met for a legitimate probability model. Now part B is a little bit different. Part B says, find the probability that a chosen person does not have AB blood, show your work, and use proper notation. And so when I'm thinking about that, does not have AB blood, what comes to my mind is the idea of complement. So the probability of not AB blood has to be the complement, 1 minus the probability of AB blood. So this was a problem that was trying to make sure, do you understand what the word not means with probability? It means finding the complement of the event. And so what we're going to do is we are going to do 1 minus the probability of AB, 1 minus 0.04, and I get 0.96. So that's the probability of someone not having AB blood. Another way of doing it, this was using the complement, which was the purpose of this problem. But if I want not AB blood, I don't want this one, I would have to then just add these numbers together. I would have to take 0.51 plus 0.26 plus 0.19. Now, if I take 0.51 plus 0.19, I get 0.7 plus 0.26 does give me the 0.96. So even that way I can check it, but this was not the approach we wanted. We wanted to have the idea that we are looking at the complement. We are looking at the probability of AB complement, which equals that. So that was the purpose behind problem 3. Now problem 4 says the partially completed table to the right shows the distribution of scores on the AP Statistics exam in a class. Suppose we randomly select a student who took the exam. Find the probability that the student earned a score of at least 3. Okay, proper notation, show your work. So proper notation. We want the probability of at least 3. So I can go about that two ways. I can find the probability of a 3, the probability of a 4, and add the probability of the 5. That's a straightforward approach. So let's try that one. So probability of a 3 we can see is 0.234. Probability of a 4 is 0.222, and we can see probability of 5 is unknown. So how do I find the probability of a 5? That's what we must do then. Well, to find the probability of a 5, I can see that this entire thing should be a legitimate probability model. So if I want to find the sum of these numbers right here, if I add all those together, and I subtract that from 1, now when I add them all together, I get 0.852. I can see the probability of a 5 then is going to be 0.148. So I can add that in. When we have all of that, we can see that what our answer is going to be, we add them all together, we get 0.604. So one way of doing it is to find this unknown right here by using the definition of a legitimate probability model. Now the other way of doing this, and a couple of students I saw did this, which was beautiful, was for them to think about what is the complement of at least 3. So look at this, 0, well, actually, no one scores a score of 0. 1, 2, 3, 4, 5. So those are my possible scores. If I want at least 3, I want everything over here. So I could find this sum and do the complement of it. So I can do 1 minus the probability of scoring a 1 plus the probability of scoring a 2. Add those two numbers together and subtract from 1. So if I realize that if I want at least 3, I can do 1 minus and think of it like the complement. So that was really interesting, and I'll write it down here, is the probability of at least 3 is going to be the complement 1 minus the probability of the sum of 1 and 2. So what do we have here? Probability of at least 3 is the complement of the probability of a score of 1 or 2. So that's actually really interesting for us to see as well. And so when they do that, if you add these numbers together, I'm going to get a 0.396. 1 minus 0.396 does give you the same answer of 0.604. So that was a very, and by the way, that is a really good approach for where we're going in future lessons, thinking of at least that way. So the students who saw it that way, that was a very great thing that they could do for future lessons. So hopefully that clarifies number 4. And the last one was problem 7, which caused a little bit of issues, and I can see why, because it says each of the paper clips in a box is either pink, blue, orange, or green. There's at least one of every color in every box. Suppose that a paper clip is chosen at random. Write these probabilities from least to greatest. So this is the tricky one, and the reason why is you have no idea of how many orange, green, how many blue, pink, etc. And that's the point. The point is an understanding of the different probabilities. And this is saying I just want the probability of orange. That's it. This is saying I want the probability of orange or blue. So let's just compare those first. If and I'll be a little bit more consistent, if I want just the probability of orange, and I want to compare it to the probability of orange or blue, well, if I'm thinking about it, the probability of selecting an orange or a blue paperclip has to be larger than just selecting an orange. If I just have, we'll put the colors in here, here's one paperclip for orange, here's another paperclip for orange. You know what? I'll put less blue paperclips in the bag. And so if I look at this, the probability of grabbing an orange is 2 out of 3. The probability of grabbing an orange or blue is 3 out of 3. So I can see right away that this probability, B, has to be greater than A. So that's good news. I know A is smaller than B, so now I need to figure out how to C relate. Now what does C mean? Well, C is almost the same idea. It's got the idea of orange, but what I want is I want the probability of orange and blue. So what does that mean? I am drawing a paperclip, one paperclip at random. So again, here are my paper clips. Again, I'm only looking at just the orange and blue just for making it a little bit easier to understand. Is if I were to draw one at random, here's the one I drew, is it orange and blue? Well, no, it's just orange. That didn't work. All right, let me draw another one at random. Here it is. This is the one I draw. Is it orange and blue? No. So wait a second. Can a paperclip be both orange and blue? And the answer is no, they can't. This has a probability of 0. Well, we do know you can draw an orange. We do know you can draw an orange or blue, but you cannot draw an orange and blue. So that would be the lowest. And we said that A is smaller than B. So CAB, C-A-B, is ordering them from least to greatest. So we had to think about the problem happening and what the different characteristics of or and really mean. And that was the purpose behind this problem. Every problem has a purpose. Is or means either one can happen. We don't care which one as long as it happens, orange or blue paperclip. And means it has to have both characteristics there, and it's impossible to have an orange and blue paperclip with just one paperclip drawn. So hopefully this clarified number 7 and helped you out with the 5.2a worksheet.